Okay, we're going to continue our study of modern physics and the beginnings of quantum mechanics, talking about something called the Compton effect. And the Compton effect is a lot like the photoelectric effect. Okay, we're going to describe it here. Okay, light hits a free electron, the electron recoils, and a second electron is produced. So it's similar, light's still hitting an electron, but this time it's a free electron, it's not stuck at a surface. And the other difference is we're going to get a second photon. I make a mistake here. Change this to photon. It is produced. So we'll draw a sketch of it right here. I have a photon coming in. I label that photon 1. I use that symbol, the gamma symbol, looks like a fish swimming down. I use that to represent a photon of light. It's going to hit this free electron this time. So label that electron. The electron is going to fly off with some kinetic energy. And then we're going to get a second photon produced. So label that photon 2. Now, as he was studying this, he realized that just like the photoelectric effect, even though it doesn't have a surface, it's still going to be a conservation of energy problem. So we're going to make a note that energy is conserved. So if I calculate the energy of this photon and the energy of this photon, okay, I can do a conservation of energy thing. The photon coming in gives up all of its energy to the electron. Some of it becomes kinetic energy, and then the rest goes into this new photon. So the energy of photon 1 gets split into the kinetic energy of the electron and the energy of the second photon. Now, Compton also looked at this and he said, wait, it's a collision. How do we handle collisions? Usually for collisions we think of momentum, and momentum is conserved. The letter for momentum, thinking back, is little p. So if I can calculate the momentums of these, I should end up with an equation that's like this. I'm going to conserve it. So momentum of photon 1 gets split up into the momentum of the electron plus the momentum of photon 2. Now there's a problem with this though. Okay? And the problem is this. When we calculate momentum, we use P equals mv. How do I do that with light since light doesn't have mass? So how can light have a momentum since it has no mass? And he had to figure out how to calculate its momentum, and he came up with this equation, P equals h over lambda. Momentum equals Planck's constant divided by the wavelength. So if I try to find the momentum of light, I'm going to use this equation. When I do the h, I want to use the joule version of Planck's constant, because that's going to give us the right units for our momentum. So on the top of the next page, we have a little example of this. All right. Photon with a wavelength of 6 times 10 to the minus 7th meter strikes a free electron. Then after the collision, the electron has an energy of 1 times 10 to the minus 19th joules. So I'm going to draw this. I have my photon coming in like this. It has a wavelength of 6 times 10 to the minus 7th meters. It's going to hit this electron, and we're going to make the electron fly off this way. We know its kinetic energy is 1 times 10 to the minus 19th joules. Okay, so copy that all down. Now, step 1, what is the energy of the incident photon? Remember, these are always conservation of energy problems. So if I have something that's not an energy, like for the photon, I have its wavelength, I have to find its energy. So step 1, we're going to use E equals hc over lambda. Okay, since the energy of my electrons in joules, I want to use the joule version of h. So that's 6.63 times 10 to the minus 34th. C is 3 times 10 to the 8th, the speed of light. And then we're going to divide that by the wavelength, which we were given as 6 times 10 to the minus 7th. And that's going to give us an energy of 3.315 times 10 to the minus 19th joules. And I might even write that on here on my diagram. The energy of photon 1 is going to be 3.315 times 10 to the minus 19th joules. Okay. Now, part 2. It says, how do we know a second photon must be emitted? Because I didn't say it in the problem, I didn't put it on my diagram, but now it's obvious that there has to be one. Why? Energy has to be conserved, and the photon coming in has 3.315 times 10 to the minus 19th. The kinetic energy of the electron after the collision is less. Where does the other energy go? It turns out it goes into this second photon. So we'll draw that in here, label it photon 2, and we're going to say that the question was, how do we know a second photon must be emitted? It's because energy must be conserved. Okay, now let's find its energy, right? So if energy is conserved, the energy of the second photon is going to equal the energy that the original photon had minus whatever it gave to the electron, so minus the kinetic energy of the electron. So it's 3.315 times 10 to the minus 19th minus 1 times 10 to the minus 19th, and that's going to give me a value of 2.315 times 10 to the minus 19th joules. So that's the energy of this second one. Now step 3. It says, what is the wavelength of the second photon? So for the wavelength, I could use this equation, E equals hc over lambda. I'm going to rearrange it, and I will get lambda is hc over E. 6.63 times 10 to the minus 34th is h. C is 3 times 10 to the 8th divided by the wavelength, or divided by the energy that we just found, 2.315 times 10 to the minus 19th. And I'm going to end up with a wavelength of 8.6 times 10 to the minus 7th. 8.6 times 10 to the minus 7th meters. I want you to notice something. That wavelength is greater than the wavelength of the original one. The original wave had a wavelength of 6 times 10 to the minus 7th. This is longer, 8.6 times 10 to the minus 7th. And that's going to happen every time because the second photon has to have less energy. Less energy is a longer wavelength. And then the last step, the momentum, we're just going to use this new equation. So step 4, we'll use P equals h over lambda. Again, every time I use this equation, I have to use the joule version of h. So 6.63 times 10 to the minus 34th over, my wavelength was 8.6 times 10 to the minus 7th. And when I do that, I get 7.71 times 10 to the minus 28th is the momentum of the photon of light. Now, I need to have units for that. If you remember back, we usually use P equals mv. And if we think about what units that's going to be, m is in kilograms, and v is in meters per second. So that's going to be my unit. Now, this makes sense because that's a very tiny momentum, times 10 to the minus 28, and that makes sense. Light isn't going, one particle of light is not going to have a lot of momentum. You're not going to get knocked over by one photon of light. Now, the next thing that comes along is this guy named de Broglie. He comes up with this very strange idea. He was a grad student in France working on his PhD, and for his PhD thesis, he said, if light, which we always thought of as a wave, can sometimes at least act like a particle, maybe things that we normally think of as particles can act like waves. So he said, if light can be both a particle and a wave, what about electrons? Can they be both as well? And he said, well, if so, it should diffract and interfere. So proof that electrons can be waves would be the following. We take an electron, shine it at a double slit or a diffraction grating, just like we do with our laser, and if it's a wave, you will get a central max, a first order max, maybe a second order max depending on the situation, maybe a third order max, and so on. But light will not light, sorry, electrons will diffract and interfere if they are waves. So if electrons can be waves, if I shine them in a double slit or a diffraction grating, I should see that electrons diffract and interfere just like light does. And he said that all of the equations we use for light should work. So for this double slit interference patterns, the equation m lambda equals d sine theta, that should work for electrons as well. And nobody knew exactly how to test it, how far apart the slits should be, or how you could make something with slits the right distance apart. So they didn't know what to do with it. So his professors actually sent his thesis to Einstein and said, what do you think? Should we award him his PhD? And Einstein said, well, I don't know if it's true or not, but it's a pretty brilliant idea. Go ahead. And it turns out when they did figure out how to test it, that electrons do produce diffraction interference pattern, so electrons can be waves. Now, the really odd thing about that is that we are made up of electrons and protons and neutrons, and de Broglie is saying those can be waves. Experimentally, it turns out to be true, so in a sense, we are made out of waves. Now, the equations we can use for this, if I want to find the wavelength of an electron, which sounds kind of weird, how can an electron, which we always think of as a particle, have a wavelength? We can use this same equation, P equals h over lambda. We can use that equation to find the wavelength of an electron. So here's an example of what is the wavelength of an electron with a velocity of 100,000. So my first step would be, I know that wavelength is related to momentum, so I'm going to find the momentum. So P equals mv. For an electron, that's 9.11 times 10 to the minus 31st for its mass. And then I'm going to multiply that by my 100,000 for its velocity. And that's going to give me 9.11 times 10 to the minus 26th for its momentum. Then I can use this new equation, P equals h over lambda. If I rearrange that, I get lambda is h over p. So it's 6.63 times 10 to the minus 34th for h for Planck's constant. And the momentum we just got was 9.11 times 10 to the minus 26th. And when I divide that out, I end up with 7.28 times 10 to the minus 9 meters for the wavelength of the electron.